All right, we're going to look at modulus argument form of a complex number and also polar form of a complex number. So let's start off with defining modulus and argument. Okay, so the modulus of a complex number is the length or magnitude of the corresponding vector on the complex plane. So if you take a complex number, say z equals a plus ib, and we've drawn it here on an Argand diagram, the length of that vector is the modulus of z. We also abbreviate that as mod z, and we write it as the absolute value of z. So you can read that as the absolute value of z or mod z. So mod z is equal to the square root of a squared plus b squared, and a simple way of thinking about that is if the length of that vector is mod z, we can just use the distance formula to work out that the distance of OP there is going to be the square root of a squared plus b squared. Now the angle that the vector makes with the positive x-axis, the angle, is called the argument of z. Okay, now that is abbreviated argz. Right, so in this case, we would just write down argz is equal to theta. Now, another thing we can deduce is that tan theta is equal to b on a, because we know that by definition, tan theta is equal to y over x. When you're thinking of a circle, there's a circle there. Think back to trigonometry, there's some sort of point on the circle of radius r, for example, and tan theta is y on x. So in this case, y is b and x is a. So tan theta is equal to b on a, and that's how we work out what theta is. So when you're trying to work out the argument, we first look at tan theta equals b on a and then find the inverse tan of that to get the argument. Now, one thing to note is arg of 0 is undefined, because if you think about it, z equals 0 is just a point, isn't it? Z equals 0 is just z equals 0 plus 0i. So that's just a point at the origin. There it is. Right, so if I said to you, what angle does that point make with the x-axis? Well, that doesn't make sense. So arg of 0 is undefined, right? You need a vector to have an argument, which means the complex number has to have some sort of length. All right, so now one thing to point out is that the argument of z has infinite many possible values for theta, okay? And that makes sense if you think back to trigonometry. If here's my ray, I can go around in a 2 pi circle there, and then I can, whatever theta is, I can just add multiples of 2 pi to that, and I can just keep going around. So you can get infinitely many versions or values for theta. So because of that, we tend to limit what theta will be. And when we limit theta to between minus pi and pi, we call that the principal argument of z. Okay, so we know that theta has infinitely many possible values. We know that for a fact. So just so we can make it more efficient, we limit theta to minus pi and pi whenever possible. That's called the principal argument of z. Now, just one other point to make is when z is expressed in terms of x and y, so for example, x plus iy here, we call that Cartesian form, okay, or rectangular form, right, because it's based on the number plane. So just be aware of that. So if there's a question saying put it into Cartesian form or put it into rectangular form, this is what they mean. All right, so let's have a look at the first example. You've got to find the modulus and argument of this complex number. So what we're going to do is we're going to do a little sketch first. Okay, so if I do a little sketch, 1 minus I root 3. Well, let's just call that 1 and minus, there we go, we'll call it, say, minus root 3 down here. All right. All right, so I've got to work out and the quarters of that will be 1 minus root 3. Okay, and that's my complex number represented by the vector. All right. Now, to find the argument, we need to look at the angle that makes with the positive x-axis. So we're looking at that angle there. Okay, theta. So let's start off with the modulus. Modulus is just the square root of 1 squared plus root 3 squared. Don't worry about the negative. And that's going to give you 3 plus 1 is 4, square root of that is 2. So mod z equals 2. Now to work out the argument, well, we know that tan theta is equal to minus root 3 on 1, which is just minus root 3. And shift tan minus square root of 3. Make sure you're in, I'd say put in degrees mode. Okay, so shift tan minus square root of 3. Okay, so you're going to get minus 60. All right, now don't forget we're going between minus pi and pi. So pi and minus pi is there. So we get theta is equal to minus 60 degrees, but we've got to make sure it's in radians. So that's minus pi on 3 there. Okay, so that's my argument. So I'm going to write down arg of z is equal to minus pi on 3. Okay, so because between minus pi and pi, don't forget this is 0. So in the negative direction, that's the angle we're after. So minus pi on 3. All right, so remember that positive angles are measured in the anti-clockwise direction and negative angles in the clockwise. Okay, so there we go. We've got the modulus is 2 and the argument of z is minus pi on 3. Okay, let's look at something called the polar form of a complex number now. Now, the polar form of a complex number is expressed as z equals r cos theta plus I sine theta, where r is the modulus of z and arg z is equal to theta. And theta is the principal argument. So if we're going to prove this, what we're going to do is consider a circle of radius r. We're going to put a plus ib as our complex number. So z equals a plus ib, if you like. That's represented on the Argand diagram there. All right. So to work out the, well, let's work out what r is first. R is equal to the square root, it's just a length there, a squared plus b squared. Okay, so that's also obviously mod z, isn't it? Mod z is equal to r, which is equal to square root of a squared plus b squared. Now, one thing we know from trigonometry is we know that cos theta for any circle, so let's just draw remind you of the trigonometry from extension 1. So I've got some point there, P, and this is radius R, xy. You would have learned that cos theta is the x coordinate divided by the radius, and sine theta is the y coordinate divided by the radius. So in this case, over here, our point is AB, the x coordinate is A, and R is just the radius. The y coordinate of our circle is B over the radius. Okay, so from those two equations, we can deduce, so let's call this equation 1 and this equation 2, right? So from equation 1, I can deduce that A is equal to r cos theta, right? And from 2, I can deduce that B is equal to r sine theta. So if I substitute that into my complex number z equals a plus ib, so we know that z equals a plus ib, then a is just r cos theta, and b is r sine theta. And then I can take out the r as a common factor. I've just got r cos theta plus I sine theta. There we go. So that's the polar form there. All right. Now, we also call that the mod arg form. So most textbooks won't call it the polar form. They'll call it the mod arg form. All right. Now, mod arg form is also abbreviated as z equals r cis theta. Just realise there's a capitalisation there. You don't need the capitalisation. It's just r cis theta. Okay, so that's an abbreviation for polar form. Now, it's called polar form because it's based on the distance and angle from the pole or the centre, right? That is the origin. So that's why it's called polar form. It's all based on distance and angle from the centre, and the centre is the pole. So let's have a look at the first example. You've got to express this in polar form. So I always like to draw a little picture here. So, little diagram. Now, minus root 2 plus I root 2, that's going to be up here somewhere. So it'll be minus root 2 there, and then root 2 there. So there's my vector. And you want to work out the argument, of course, and the modulus. There's my argument. So, and obviously that's got coordinates minus root 2 comma root 2. So I'm not going to worry about the negative sign there for the modulus. It's going to be the square root of root 2 squared plus root 2 squared. Right, root 2 squared is 2. So it's just going to be root 4, which equals 2. So the modulus is 2. Now for the argument, let's have a look at that. One way to figure this out. So I can work out the acute angle here. Let's call that alpha, if you like. Now, I know alpha is an acute angle, so I could say tan alpha is equal to, now if I'm looking just at the acute angle, then it means I'm just looking at distances. That is root 2 there, and that distance there is root 2 there as well. So tan alpha will be root 2 over root 2, which is just 1, okay? And that means alpha will be pi on 4. Right. Now, once I've got that acute angle of pi on 4, I can then work out that the arg of z will be pi minus pi on 4, which equals 3 pi on 4. Okay. Now, just be aware for the calculator fanatics. If you did this for this question, there's a bit of a danger here. If you said, all right, no problem, tan theta is equal to root 2 on minus root 2, which is minus 1, and then you went shift tan minus 1 to give you negative pi and 4. Now, there is a problem with that, of course. Negative pi and 4 is in this quadrant here. Okay? It's not going to give you the correct argument. So my advice is to find the acute angle first, just using positive distances, because don't forget, for an acute angle, you're always going to get a positive result, right? Positive trig ratio. So find the acute angle and then find the angle of any magnitude. This comes back to extension 1 theory. Okay? Let's have a look at the next one. So that's wrong, by the way. That obviously theta is not correct. So don't do it that way. Now, next one, same again, draw a diagram. By drawing the diagram, you won't make the mistake of putting the argument in the wrong quadrant. And minus 1 minus I root 3, that's going to be down here somewhere. Okay. Coordinates of that will be minus 1 and minus root 3. Right. Now remember, we're after the principal argument here for polar form. So that means you want this angle here. That's what you want. Now, probably the easiest thing to do first is just work out the modulus. So the square root of, I'm not going to worry about the negatives there. 1 squared plus root 3 squared. And again, that's going to be 2. Okay. Now, let's work out the acute angle between the ray and the x-axis. This one here, I'm going to call it alpha. Right. I'm going to use this right angle triangle. Now, this distance here, that's root 3. That's a distance. And this distance here will be 1. All right. So we know that tan alpha is equal to root 3 over 1, which is just root 3. Okay, now if you work that out, that's going to be 60 degrees, which is just pi on 3. Okay, so the acute angle is pi on 3, which means the argument that you're after, don't forget the argument is theta, the argument that you're after is there. So arg z will be, right, now if this is alpha is pi on 3 there, then arg z must be minus 2 pi on 3. Okay? And again, if you tried just using your calculator off the bat, you'll get an argument of pi on 3, and actually the argument is minus 2 pi on 3. So you've got to be aware of which quadrant you're in, okay? And use your angles of even magnitude. Okay, for the next one, let's do another sketch. All right, so here we go. Minus 2, 6, it's up here somewhere. There we go, that'll do. Not to scale. Minus 2, 6. Now the argument you want again, let's mark that in, it's got to be with the positive x-axis. There it is, between pi and minus pi. So let's work out the modulus first, that's the easiest part. Again, I'm just going to ignore the negative sign there. All right, that's going to give you root 40. I'm not going to abbreviate that, I'm just going to leave it as root 40. That's the exact modulus. Now, to work out the argument, I'm going to work out this angle here, alpha, the acute angle. So I'm just going to form a nice little right angle triangle. I'm just using distances because I'm using a right angle triangle. So this distance here will be 2. This distance here will be 6. Okay. Now, tan alpha will be 6 on 2, right, which is 3. Now, if you work that out, so shift, I'm in degrees mode, shift tan 3, you're going to get 70. Let's round it to the nearest degree. It's about 72 degrees, okay? Which means the argument, right, will be 180 degrees minus 72 degrees, which is 108 degrees, but we know arguments are expressed in radians. So you've got to convert that to radians, okay? So times by pi on 180. Right, 1.89 or 1.9 radians. Okay, 1.9 little radian symbol there. Okay. So there we go. That's approximately. I should say that's an approximation. R equals Z is approximately that and approximately that because we've rounded. Okay. All right. Next one is to express this in polar form. Now, just realised I haven't expressed the others in polar form, but we'll come back to that. Let's come back to the others now. It's a bit late at night. Okay. Coming back to the first one, just putting this in polar form, it's going to be 2 and then brackets cosine of 3 pi and 4 plus I sine 3 pi and 4. I'll read the question next time. This one here, it'll be Z is equal to 2 cos, now be careful here, negative 2 pi on 3 plus I sine, running out of room here, negative 2 pi on 3, close bracket, okay? Now the question 3 here, putting this in polar form, let's just use an abbreviation. So we're going to have root 40 cis 1.9 radians. And I'm just going to put the approximation symbol there. Okay. Now what about this one here? This is not quite in polar form, is it? Because if we expand those brackets, actually we can see here we need a plus sign. Now, we are going to use an identity here, which you might have seen before. Sine of minus theta is equal to minus sine theta. Okay, so that means minus sine pi on 6 is just sine of minus pi on 6. Okay, so that means we can write this down as Z is equal to 2 cosine. The other thing we should, before we do that, not quite ready for polar form. The other identity we know, let's just change colours here. The other identity we know is that cosine of minus theta. Right, just think back to your ASTC rules. So you would have done these identities before. Okay, cosine of minus theta is equal to cosine of theta. Okay, so that means I can express the number here in polar form. So this is going to be 2. Just use square brackets here for a variety. I'm going to write cos of pi and 6 as cos of minus pi and 6. Is their equivalent? Plus I sine, because taking back to this, minus sine pi and 6 is the same as sine of minus pi and 6. There we go. So that's in polar form now, because we need to have the angles the same, right, for each term. And we need a plus sign there as well, between the cosine and the sine term. Okay. Now, last question, I think. Yeah, last question. Got one more proof to do as well. Now, we've got to express this in Cartesian form. Now, Cartesian form, if you remember, is x plus iy form. Okay, which means we've got to work out. Let me just get rid of that. I'm just going to work out what cosine of 5.3 is first. So let's do that. Cosine of 5 pi on 3, right? If you like working in degrees better, you could convert that to degrees. Right, that's cosine of 300 degrees. Right, and then if you work that out, 300 degrees is down here somewhere. There we go. There's your 300 degree angle, which means that's 60 in there, isn't it? So if you're looking at ASTC, cosine of 300 is also equal to cosine of 60, isn't it? So it equals cosine of 60 degrees. And then if you think back to your circle, 2, 1 root 3, 60 in there, 30 in there. So cosine of 60 is a half. So sorted that out. The next thing you've got to work out is sine of 300. Well, sine of 300, because sine of 5 pi and 3 is sine 300. Sine of 300, well, we know that sine is negative in the fourth quadrant, so it's minus sine 60 degrees, which now sine of 60 is root 3 on 2, so just minus root 3 on 2. So if we sub that back in here now, so z equals 2 brackets cosine of 5 pi and 3 is a half, and plus I, sine 5 pi and 3 is minus root 3 on 2. She's just thinking I wouldn't normally write it like that. I'd normally just have minus I there. Now if I expand those brackets, I'm going to get 1 minus I root 3. That's it. Okay. So that's the answer for that question. But I just realised it's not a 2, it's a 3. Okay, I've got to get new glasses. That's all right. Fix this up. 3 there. Okay. All right, that'll change my answer. Here we go. 3 on 2 minus I 3 root 3 on 2. There we go. And that's done for that question. Right, that's in Cartesian form now. Okay. Yep. All right, so let's have a look at the last property, conjugate in polar form. Okay, so the conjugate, Z with a little horizontal line above it, is r cos theta minus I sine theta, which can be written in the form r cos of minus theta plus I sine of minus theta. Now, it's very similar to what we just did then. Let's just say I've got, I know my identities already, don't I? So I'm just going to say, well, look, I know that cos of minus theta is equal to cos theta, right? So think back to, let's just say, there we go. Let's say that there's minus theta there, ASTC, right? So cos of minus theta, and so these identities, you've seen these before, minus sine theta. Okay, so that means if I can write r cos theta minus I sine theta as r, then cos minus theta. Now minus sine theta, it's just sine of minus theta. Okay, so that's it. And that's the conjugate. All right, so that's how we can write the conjugate. All right, and that's our lesson for today.